Hi everyone, myself Navyatha, working as Assistant Professor in the Department of Cybersecurity and Data Science in MLR Institute of Technology. Today I am going to discuss about the topic finding the keys using closure. The overview of my presentation includes finding the keys using closure and the examples to find the number of candidate keys. So already we have discussed about functional dependencies and how to find these functional dependencies in our previous sessions. Now we have to find the closure to obtain some super keys or else candidate keys which we have already discussed in our previous sessions, the different types of keys. What are the generally basic different types of keys that we use in DBMS? Primary key, candidate key, super key, foreign key. These are different types of keys that we use. Generally, these are the main keys that we use to deal with DBMS. So, what is the primary key that we all know, which is used to obtain the values uniquely? That column or that attribute is considered as primary key. So, what is the candidate key? Here, two or more keys can be considered as a primary key. Right? What is the super key? If at all we used to consider whatever the columns, by considering all the columns, all the attributes, not any restrictions, right? That is what here super key. For example, let us discuss these keys in a short manner. Let us consider SID, yes name, yes mobile number, right? So here SID, yes name is XYZ, S mobile number, some 9626428, some so on, right? Next, ABC, so on. So here what can be a primary key? The key that derives some data uniquely. That is what a primary key. So SID can be a primary key. So primary key can be what? SID. So what can be a candidate key? If at all with the help of this primary key, some more column can be added which can be derived the data uniquely. So here the candidate key is nothing but SID comma S name. This can be with the help of primary key. With the help of these two, we can derive the data uniquely. Right. Next, this is the short method. Right. Next, what is super key? Super key. So by considering all the attributes, that is nothing but SID comma S name comma S mobile number. By considering all the attributes, we can retrieve the data uniquely. That is what super key. So we can say that minimal super key can be a candidate key. What? So candidate key is nothing but what? Minimal super key. Minimal super key. That is what here candidate key. Right. And the minimal candidate key can be a primary key sometimes. Right. So that is what the brief discussion about the keys. And here we can find the number of candidate keys and the number of super keys for a given dependencies, functional dependencies. Why? What is the necessary to know about this concept? Because for further concept, that is what the normalization, which is the heart of DBMS, for that concept, we used to learn about how to find super keys, candidate keys for the given FDs. That is what the thing. So here, the finding the keys using closure. That means we have dealt with closure in our previous session. For example, let us discuss functional dependencies. A tends to B, B tends to C. A tends to B, B tends to C. Right. So what is here closure? Closure means what? What this one or what F derives, F closure, which includes all the dependencies, and from these dependencies by using axiom rules we can derive further more dependencies. That is what closure. So closure means what? So F plus which includes what? A tends to B, B tends to C. That is what the dependencies or the functional dependencies which are already given, we have to include those things. Just right. Next, from these dependencies we can derive some more functional dependencies by axiom rules. Right. So here A tends to B, B tends to C. we can derive A tends to C by transitivity, by transitive property. Clear? So this is what the closure of this F. So in this manner, we can able to find out the closure. By using this method, we can find how many super keys, how many candidate keys can be available. Clear? And some more examples to find the number of candidate keys. So what are the prerequisites we required, right, about to go further about this topic? So what is the super key? What is a candidate key? The basic definitions here. If closure result of an attribute set contains all the attributes of the relation. For example, this is the relation which contains these attributes. This is the given relation which contains these attributes. So, for example, let us find the closure and which contains all the attributes here. If at all I found the closure and that closure the resultant of the closure contains all these attributes, then it can be called as what? Super key. Right? So, if closure result of an attribute set contains all the attributes of the relation, then that attribute set is called super key of that relation. Thus, we can say that the closure of a super key is entire relation schema. This is what the definition about the super key here. And what is the candidate key? If there exists no subset of an attribute set, whose closure contains all the attributes of the relation, then that attribute set is called as candidate key. Here, this definition might be somewhat a little bit confused manner, but after seeing the example, then you can will get an idea about this definition. Clear? So, let us deal with these two definitions after representing one example. Let us go for example, and before going to do that example, have to find the number of super keys and candidate keys for the given FTs. We have some steps, right? What are those steps? So, here consider all the attributes and find the closure, which is the super key. For example, R of relation ABCD they will give. It contains all the 4 attributes. We have to, our first step is what? We have to find the closure of all these attributes. That is what the first step. What is the second step? We can discard the attributes which are derived from other attributes from the given FDs. Along with this relation schema, they will give some set of FDs, and with those FDs, we can discard these closure set. That I will explain clearly while explaining the example. Next, what is step 3? Find out the proper subsets of above obtained closure to determine it is a candidate key or not. Here CK means what? Just I have written the shortcut method, candidate key. Whether it is a candidate key or not. And what is the step 4? To find more candidate keys, check whether the prime attributes are available in the right hand side of the given FDs and replace with those attributes. So what are here prime attributes? In the above step, we found as a candidate key, right? For example, we have obtained AB is a candidate key. Then, what are the prime attributes here? A, comma, B. These are nothing but the prime attributes. So, this will be explained or else will be understood clearly by you people with the help of example, by considering one example. So, see, this is the example. Consider the relation, and this relation contains 5 attributes A, B, C, D and E. And what are the FDs given here? A tends to B and D tends to E. These are the given FDs which are already given. Now what is our first step? This is the relation which contains, we have to find out the closure of all the attributes here. That means we have to find out the closure for A, B, C, D, E. So what is the closure for A, B, C, D, E? Here we have to include all these attributes. What are these attributes? A, B, C, D, E. And we need to see that whether A derives B or not, like that. Okay. Here we have included all the attributes. A derives B. Yes, B is also included. Next, What are the attributes here? C is derived by anything? No. Next, D derives E. This is also included. So, we have included all the attributes here. That is what our first step. Clear? Next, we need to discard. What is the discarding here means? See here in the left hand side, this part, here from the given FDs, A derives B. B is derived by A. Right? So, we can discard B. Why? Because A derives B or B is derived by A. So, here we can, now we'll get the closure ACDE plus. Right? ACDE. So, what is the ACDE of closure? We have to include all these attributes ACDE, and we need to check A derives what here? A derives B, we need to include that one. C derives anything? No. D derives anything? E, yes, we have already included. B derives anything? No. So, this is what the closure for ACD. Again, we need to check whether in this closure set we can discard anything. Right. So, here D derives E. D derives E. So, we can discard E. Why? Because E is derived by D. Okay. So, we can find out ACD. Now, we have to find out ACD plus. Closure set of. This is the attribute set. Clear? This is the attribute set ACD. And after discarding E, we obtained ACD. So, here we need to include these attributes. Whatever the attributes here A, C, D. And we must also check that from the given FDs. Whether this A derives anything. A derives anything? Yes. A derives B. C derives anything? No. D derives anything? Yes. D derives E. That is also must be included. So, in this way we have find out ACD plus. Again, we need to check whether we can derive or whether we can discard anything from the given dependencies. So, A is derived by anything? No. C is derived by anything from the given FDs? No. D is derived by anything? No. So, with this, we have obtained one super key. This is nothing but a super key. ACD plus is nothing but a super key. Why I am telling a super key? Why? Because here in this, we have obtained all the keys which are represented in the relation. Super key is what? By considering all the attributes from a given relation schema. So, here we have obtained all the attributes in the relation. So, here this ACD is a super key. Clear? Now, we need to check the candidate keys now. How to find out the candidate keys? What I said, candidate key is nothing but it is a minimal of a super key. Right? Minimal of a super key. That means here we have to find out the proper subsets of this super key. Proper subsets. So, what are the subsets here? ACD. AC can be one subset, AD can be one subset, CD can be one subset, right? These are nothing but the proper subsets of this particular set. This is the particular given set. For example, in a particular set, ACD, we need to find out the proper subsets. So, AC is a proper subset of ACD, AD is a proper subset of ACD, CD is a proper subset of ACD, and next, A is a proper subset of ACD, C is a proper subset of ACD, and D is also a proper subset of ACD. So, before going to know this, you need to know what is a subset, what is a proper subset, like that. So, let us discuss that one with a simple example here itself. For example, A is here one set, S is equal to ABC. S is equal to ABC. Q is equal to BC. Q is equal to BC. Check now whether Q is a subset of S. Q means what? This one. This is a part of S. Yes. This is a part of set S. Q is a subset of S. Then what is the proper subset? So, if at all, in this example, I have included A. Right? So, now we can say that ABC, Q contains what here? I have included just now ABC. Q also contains ABC. And we can say that now Q is subset of S. Yes, it is a subset of S. Why? Because it is itself a subset. Right? So, Q is subset of S. But in this case especially, here we need to represent Q is subset or equal to S. Why? Because here the elements are equal. Number of elements are equal. Number of elements are equal. So, Q is subset or equal to S. So, this is what? A subset. But it is not a proper subset. Only if Q contains lesser elements than the given set and it must be subset of the given set. Then only it is nothing but a proper set. That means, so in this example, let S is equal to ABC, Q is equal to BC. Then we can say that Q is a proper subset of S. That is what here proper subset meant for. Clear? Now, so in this manner, we obtained a super key here. We obtained a super key. We have to find out the number of candidate keys. What is a candidate key? It is nothing but a minimal super key. So, we need to find out the proper subsets of this one. So, ACD. From this, what are the subsets here? AC, AD, CD, A plus, C plus, D plus. So, now find the closure. AC. AC means what here? We need to include A, C, both the attributes, and whatever the attributes that are derived by these two. A derives B. C derives anything? No. So, this is what? The closure. In the same manner, I need to derive AD plus. So, AD means what here? I have to include AD, and A derives what here? A derives B. D derives what? D derives E. So, I have obtained AD, BE here. In the same manner, we need to find out all these closure. Right. And if at all you observe one thing here, I have found out all the things, all the closures of these sets. So, whether these set contain all the attributes? No. Why? Because our relation contains 5 attributes, A, B, C, D, E. Our relation contains 5 attributes. Any of these subsets contain all the 5 attributes here? No. Right. So, here D is missing and E is missing. In this C is missing. So, that is what here we can say that now ACD are not having a super key. Therefore, it is a candidate key. We can say that it is a candidate key. Why? Because here the proper subsets of this super key doesn't contain all the attributes. So, it can be a candidate key. You can see now the definition. So, what is the definition here? If there exists no subset means we have found, right, in ACD plus for AC, AD and CD, A, C, D. These are subsets, right? These are different subsets. So, from each no subset of an attribute set whose closure contains all the attributes of the relation. In each and every resultant, we doesn't find all the attributes. Then it can be considered as this can be considered as a candidate key. That is what the definition. Hope you understood now. If there exists no subset of an attribute set whose this closure contains, the subset must not contain all the attributes. Then it can be called as what? A candidate key. Now the question will be whether only this can be considered as a candidate key. Whether only ACD can be considered as a candidate key. No, there must be. For example, BCD can be a candidate key, ACD can be a candidate key, and ECD or else CD. There are many from these probabilities, many number of probabilities, right? So, here we have to find out how many candidate keys can be possible for this one. We have found only one till now. That is what? ACD. ACD is a candidate key. So, now to find more candidate keys, here we need to check the prime attributes available in the given FDs or not. What are prime attributes? Here comes the concept of prime attributes. So, whatever the attributes are there in a candidate key, here this is a candidate key, right? Here ACD is a candidate key. We found that ACD is a candidate key, and what are the prime attributes here? Prime attributes are the attributes which are there in the candidate key. So A comma C comma D, these are nothing but what? Prime attributes. You need to check whether these prime attributes A, C, D are available at right hand side of the given FDs. These are available at right hand side of the given FDs. So what are the FDs given here? A tends to B, D tends to E. A tends to B, D tends to E. These are the given FDs. And we obtain prime attributes A, C, D. Whether A, comma, C, comma, D are there in right hand side of the FDs, A, C, D? No. Right, in right hand side of the FDs. That means here. Here we need to check whether prime attributes are available in the right hand side or not. No, not available. Therefore, we can conclude that this is the only candidate key available for this relation, ACD. Only candidate key. So, what, if at all ACD is available in this right hand side, then what we have to do? That will be discussed in our next example. Okay. So, this is what we have done. So, here see, but we cannot say only ACD is the candidate key. There can be any number of candidate keys. So, here comes the concept of prime attributes. So, what are the prime attributes here? Whatever the attributes that are there in the candidate key, those attributes are called as prime attributes. So, prime attributes are those attributes which are a part of candidate key. Here CK means candidate key. Now, we need to check whether this ACD are available in the right hand side of the given dependencies. Whether these ACD are available at the right hand side of the given FDs. No, right. So, since we cannot find any ACD in the right hand side, we can conclude that ACD is the only candidate key for the given relation. Now, let us do the same procedure to find out the super key and candidate keys for the given next example. See, consider the relation ABCD with the functional dependencies. Whatever the dependencies here given, A tends to B, B tends to C and C tends to A. Now, what is the first step here we need to find? We need to find the closure for all the given attributes. We need to find the closure for all the given attributes. That is ABCD plus. So, ABCD, we need to include all the attributes in the relation ABCD and we need to include further more attributes. What here A derives what? A derives B. That has been included. B derives C, that also has been included. C derives A, that also has been included. D derives nothing. So, this is what the key obtained. What is the next step here? We need to discard the left hand side part by considering the FDs here. Right. So, here from the first given FD, A derives B. Here, A derives B. A derives B means B is derived by A. So, we can discard B. Why? Because A is deriving B and B is derived by A. We can discard B. So, we can obtain ACD closure. Now, we have to find ACD closure. What will be the ACD closure? We need to write all the elements here ACD and we need to represent whether A derives anything here from the given FDs. Yes, A derives B and C derives anything. C derives A, that has been already included. B derives C, that has already included. D derives nothing. So, this is what we have obtained. Next, again check whether ACD, in this we can discard anything. Right. So, here from the given FDs, see here A derives B and B derives C. We can say that A derives C by transitivity, one of the axioms rules that which we have discussed in our previous sessions. So, if at all you don't know, please go through that sessions also. Okay. So, by transitivity here, A derives B, B derives C, then we can say that A derives C. Right. So, A is deriving C here indirectly. So, we can discard C here. Right. So, why? Because from this axiom rule, A derives B, B derives C, we can say that A derives C. So, we can discard C. Now, we can obtain AD closure. AD closure means what? AD we have to include. Next, from the given FDs, A derives B and B derives C and D derives nothing. So, this is a ultimate. Whether we can check whether AD derives, we can able to discard some more attributes from the given FDs. Right. So, here let us check. A is derived by anything? No. D is derived by anything? No. So, with this we can stop. This is what here a super key. Why? Because we have obtained A, B, C, D, all the attributes in the given relation. This is what super key. Now, what is our job? Our job is to find out the candidate keys. Next step is to find out the candidate keys. So, what are the candidate keys here? So, the proper subsets of the super key. So, we have obtained AD plus. Now, AD plus. This is what we have obtained. So, in this, what AD, BC. These are the attributes AD, BC, right? And what are the functional dependencies here? A tends to B, B tends to C, C tends to A. A tends to B. This is for reference I am writing. A tends to B, B tends to C, C tends to A. C tends to A, right? Now, what is our step? We have found out the super key and now we have to find out the minimal superset. That is what here? A closure, D closure. Let us obtain this one. This is what the superset, right? AD, right? So, A closure, D closure. So, A closure means we have to include A. So, whether A derives anything? Yes, A derives B. Whether B derives anything? Yes, B derives C. C derives anything? A, which has already included. So, enough, right? Next, D. We have to include D. Whether D derives anything from these dependencies? No. So, only D. So, these subsets does not contain all the attributes. That is why it is called as a candidate key. Here, one key which I have obtained, that is what AD, candidate key. Clear? Why? Because the proper subsets that doesn't obtain all the attributes in the given relation. That is why it is a candidate key. Next, we have to find out, this is the only first candidate key we have obtained. With this, we can't stop. We need to check whether some more candidate keys are available or not. What is that step? Here, we need to find out whether these prime attributes, whatever the attributes that are there in the candidate key are called as what? Prime attributes. We need to check whether these prime attributes are available at the right hand side of the given FDs. Right hand side of the given FDs. AD. See, check whether A is available at the right hand side. Yes, it is available here. Right? So, we have to replace. This A is derived by what? C. This A is derived by what? C. So, here we need to replace this A with C and D as it is. Okay. Now, see here, what I am going to tell you is, you need to check whether these two prime attributes, any one of the prime attributes, check from left hand side, okay? From any one of the prime attributes available in the right hand side of the FDs. Check here, A. A is available in the right hand side? Yes, it is available. So, A is derived by which one? C. So, you have to replace it with A with the C. Okay. So, this is what the second candidate key. Let us check. Right, CD. Whether it is a candidate key or not. You need to check. So, CD closure. CD closure. Okay. So, here the proper subset. CD means what here? C. Proper subset C, D. Right. So, what is here? C. C derives what here? A. A derives what here? B. B derives C. Okay. Next. D closure. D closure means only D. D derives nothing here. Okay. And before going to find out these proper subsets, check whether this is a super key or not. Why? Because if we obtain a super key, then only from that we can obtain candidate keys. So, here we have to include CD. From C derives A derives B. We have obtained all the attributes. So, here CD is nothing but a super key. So, from this super key, we need to find out a proper subset, whether it is a candidate key or not. Right. So, here CD and the proper subsets doesn't contain all the attributes. So, therefore, CD is a candidate key. Check whether these attributes are available in the right hand side of the given FTs. See here C. C is there in the right hand side? Yes, it is available. C is available. So, by which attribute we need to replace this one? C is derived by B. So, replace this C by B. Right. So, this is the procedure to find out the more number of candidate keys. Clear? So BD. Let us find BD. BD closure first, whether it is a super key or not. Yes, BD. B derives C and C derives A. All the attributes have been obtained. So it is nothing but a super key. Now what is our step to find out the candidate keys? So what is the candidate key? We need to find the proper subset D plus. Whether to check whether it is a candidate key or not, we need to find the proper subsets. So and this proper subset, in this proper subsets, we must not obtain all the attributes. So what is B plus B? B derives C, C derives A derives B. This is what, and what is here? D. So this is a, why? Because here we doesn't obtain all the attributes in the given relation. So this BD can be a candidate key. Now check whether BD is available, B or D is available at the right hand side. B is available. B is available and it must be replaced by A. And it must be replaced by A. AD. AD we have already obtained. Right? AD we have already done. So with this, we need to stop the process. And in this format, we can able to find out the number of candidate keys. So that is what here. How many number of candidate keys we obtain? AD for this given relation, AD, CD and BD. These are the 3 candidate keys for the given relation. Right. So in this manner, we used to obtain the number of candidate keys for the given set of FDs and the relation. So what we have discussed in this session, first of all, we need to find out, have to find out the closure, right? From that closure and from that given FDs, have to find out the super keys, and from that super keys, how we have to find out the candidate keys, and have to find out the number of candidate keys by replacing the right hand side part, right? So these are the things which we have discussed today, and in the next section, let us discuss about the normalization concept, which is nothing but the heart of DBMS. And for this normalization concept, we have discussed all these things now. Thank you.